Hey guys, welcome to Unit 1 Atomic Structure, Section 1 Atoms. Okay, so now we're going to really dive into the periodic table. So you're going to start understanding a little bit more about the periodic table by understanding how it's organized and understanding all the stuff that's on it, okay? Elements are substances that really you can't break down any further. They are made up of smaller particles, but those particles are not specific to that element. So the combination of the subatomic particles, which we'll talk about in a few minutes, that's what makes the element itself. It's organized on the periodic table, and a very good point to make is that if something has the same number of protons as something else, then it is the same element. So that is how we organize things on the periodic table. They are organized by the number of protons, and we'll talk about protons in just a minute. So again, the periodic table organizes the elements, and it is organized by atomic number or number of protons. So if you've ever looked at the periodic table, you might notice that over here on this side of the periodic table is element 1, then element 2, 3, 4, 5, 6, 7, 8, etc. Okay? And it basically reads like a typewriter. You read across each row, and the numbers all match. So that is how it is organized, is by atomic number. Now the periodic table is organized in groups vertically, and we'll talk about that in Unit 2. Every element has an abbreviated chemical symbol. The chemical symbol for oxygen is O. Well, okay, we're writing the black on the black background. O. The chemical symbol for nitrogen is N. The chemical symbol for hydrogen is H. Okay, but some symbols actually have more than one letter. Usually it's one letter or two. Things like sodium, Na, or calcium, Ca. Okay, not to be confused with carbon, which is C. Okay, so that's why we have different symbols for them. The first letter is always capitalized. The second is lowercase, and the letters usually represent the substance's name, or in the case of sodium, Na, which it is reflective of its original Latin name, which was natrium. Everything that is not pure energy is matter, and in that case, that means that it is made up of atoms. Now, of course, some of you are going to say, well, wait a minute, what about antimatter? Well, that can be a question for your physics teacher. I don't do all that, okay? But the basic unit of matter is the atom, so everything is made up of atoms. The atom has two parts, the nucleus, which is the central part of the atom, very similar to the nucleus of the cell, which you may remember from biology, and the electron cloud, which is a area in which you would find the electrons around the atom. Now, we're going to find out later that it's not a perfectly organized area, but it is a general area that you're going to find all the electrons orbiting the nucleus. So this is kind of a good diagram to explain the nucleus and the electron cloud. So right here we would find the nucleus, C-L-E-U-S, and you see that the cloud, while a lot of times we see, oh, there's the nucleus, and we would see, oh, it has these rings around it. Well, there are levels of energy around the atom, but when we get into the next section 3, actually, you're going to see that those levels are not really as cut and dry as you might think, and instead we tend to believe that the electrons surround the atom really just in this cloud-like formation. So it's just kind of an area in which you might find those electrons. So again, the nucleus is found at the center, and it is made up of protons and neutrons. And we're going to break those down in just a minute, but the basic definition there is that the proton is a positively charged particle. The neutron is a neutral particle, or a no-charge particle. As a result, when you put positives and no charges together, the nucleus is going to end up with a positive charge. So across the board, the nucleus has a positively charged, and it is very, very dense. There's a lot of matter, relatively speaking, in that very, very small area. And I guess you wouldn't say matter, since matter is made up of atoms, but there's a lot of stuff in that very small area, so it is very densely packed. So this is going to be one of those slides that I would just pause and write down the slide, okay? But these are the subatomic particles. Subatomic meaning below the atom, subatomic. And these are the particles that make up the atom. Now, we're not going to go into as much detail as you might get in AP or IB chemistry in terms of quarks and neutrinos and antineutrinos and antimatter and all of that stuff. We're just kind of looking at the basic subatomic particles, being the electron, the proton, and the neutron. Okay? In this particular chart, you can see that the electron is represented with an E. I usually just write it as E with just a little negative charge up there, but the 1 is okay. The negative charge is indicative of 1, so it just basically means the same thing. It has a -1 charge. It has a mass that is very, very small, and this AMU is the atomic mass unit. It was created to determine mass of atoms. So it is a very, very small unit, and the electron has almost no mass. It is extremely small. And again, it's found in the energy levels or electron cloud outside the nucleus. Protons have a positive charge. They have about a 1 AMU, and they're found in the nucleus. Neutrons have a neutral charge, 1 AMU, also in the nucleus. So if I'm looking at the mass of the atom, most of it is comprised of the protons and the neutrons, okay? The electrons are not really factored into the mass of the atom. So when we start calculating mass of the atom, we're only going to be looking really at the mass of the protons and the neutrons. I also wanted to throw it in here because we're going to start talking about it, but we will get into it more heavily later. The idea of the valence electrons, we said that electrons are found in the energy clouds or in the electron cloud. They are at set energy levels from the nucleus, so distances from the nucleus. And so the ones that are found at the outermost energy level, those are called the valence electrons. Those are the ones that that the atom is going to gain or lose. They're also the ones that it's going to use when it's bonding. So we'll kind of be throwing that word out there. I wanted to make sure you understood the vocabulary term because like I said, I will be using it periodically. And this diagram is pointing to the valence electron for lithium, which is the one on the outermost ring. So as mentioned, the nucleus is very dense, so that's where you're going to find most of the mass, but not the vast majority of the size. The electrons, while they are very small individually, they spread out. Okay, so they are spread out in that electron cloud, so that the electron cloud, and I guess I should say that, the electron cloud is the largest region of the atom. Individually, the electrons are very small, but when they're whirling at a very high speed and they're spreading out a little bit around the atom, that area is going to become very large. So in reading the periodic table, generally most periodic tables are going to have an element symbol, the element name, the atomic number, and another number, which is the average atomic mass. In this particular case, we're just looking at atomic number, which is the number of protons. It is always going to be the smaller number in the box. For carbon, it is 6, okay? Now, when we talk about mass, remember I told you a few moments ago that mass is the protons and the neutrons combined, okay? Well, that means that the mass, the average atomic mass, and you'll see it on the next slide, always is going to be higher than the atomic number. Well, that makes sense because average atomic mass is protons plus neutrons plus something else, which I'll talk about in a minute. But it's really the mass of the protons and the neutrons for an atom, and the atomic number is just the protons, so it should always be smaller. Again, the average atomic mass is the average mass of all the isotopes, new word, we'll get to that in a moment, of that element, taking into account the percent abundance of each, okay? So what that means is that not every carbon on Earth is exactly 12 it has exactly 12 as a mass, okay? Some of them have 13, some of them have 11, some of them have 14, okay? And those are isotopes of carbon, and I'll define those in just a few minutes. But what we're really looking at when we're looking at the average atomic mass is, let's say that carbon 12 makes up 99% and carbon 14 makes up 1%. Now this is a lie, so don't quote me on this. I just made that up. If that were the case, we wouldn't just add 12 and 14 together, divided by 2, and get an average, because that's not fair since carbon 12 makes up 99%. In the next section, we're going to be actually looking at how we calculate average atomic mass. I just wanted you to know that that number, the reason it's a decimal and not a perfect number, is that it does, in fact, take into account the percent abundance of each, okay? And I put a note over here that the mass number, which is protons plus neutrons, which we'll talk about in a minute, is not directly found on the periodic table because mass number is exactly protons plus neutrons for a specific atom. Mass number is specific to an atom, okay, or to an isotope, whereas average atomic mass is specific to that element, okay? So looking at protons, neutrons, and electrons, protons is always my atomic number, so I can find it there. Electrons should usually be the same, okay? And I'll talk about that in a minute, why. But they should both be the same. Neutrons is going to be the atomic mass, or rather the mass number of the atom minus the atomic number. So if I had carbon 12, then I would say 12 minus 6 is 6 neutrons. Okay, so that's generally how I do, and I know that I don't want to say this rounding atomic mass first. I put it on here, but it really isn't perfectly true. So I'd rather you know that if I have the mass number, I just subtract the protons. If I don't have the mass number, I need the mass number, okay? Because mass number is protons plus neutrons without taking into account the relative abundance of the different isotopes. So you need that mass number in order to figure it out. In this case, we're going to look at the mass number as being 197, subtract the protons from it, that gives you the neutrons. The general charge of an atom should be neutral, because if you remember, if I have protons, which are positive, plus, plus, and plus, and I have electrons, which are negative, 3 and 3, I should end up with a neutral atom because the positives and the negatives cancel each other out. So as long as the protons and the electrons equal one another, I should have a neutral atom. Now that's not always going to be the case, but as long as they do equal one another, I should have a neutral atom. Because if I were to take 3 pluses, okay, so these are my protons, and I were to take my 3 electrons, okay, pair them up, bloop, bloop, what I end up with is an overall 0 difference. There's nothing left over. And so in that case, this is no charge, okay? Now you're going to find out that at some point you can gain and lose electrons, which would change the charge of the atom, and those are going to be ions. We'll talk about those later. But as long as the protons are equal to the electrons, it should be a neutral atom. Okay, so I want to teach you right now how to write the isotopic symbol. This right here is the isotopic symbol for a beryllium ion. Okay, so in this case we have beryllium, Be. So we have the symbol. That's where you start an isotopic symbol, is by putting the chemical symbol. Okay, and then you're going to see that there's really 3 areas that you can put something. Okay, you have the symbol in the middle, that's obvious, and then you have on the left-hand side a number on top, a number on the bottom. On the right-hand side, there's possibility for a charge. This is not always present. Okay, if you don't have a charge, you don't write the charge. But if there is a charge on the atom, you would write it. Okay, and if you're like, wait, how do atoms get charges? Just wait, we're getting there. Okay, the mass number is our number of protons plus our neutrons. So you can only really do that for an individual atom. You can't use the average atomic mass because that takes into account the relative abundance of all of the isotopes. But for a particular atom, if you have the mass number, that number goes up top. The atomic number, or the number of protons, goes on the bottom. Okay, so those are the kind of 3 locations. So let's do some practice. Okay, so sodium atom with 11 protons and 12 neutrons. So sodium, okay, sodium is Na, and remember we can put 2 numbers on the left or 1 on the right. Okay, number of protons is 11, so that goes on the bottom. On the top left is where we're going to put the mass number, which is protons plus neutrons. Okay, so in this case, that's 11 plus 12, which is 23. I see no indication of a charge difference, so that is my isotopic symbol for this particular atom. Okay, looking at another sodium, Na has 11 protons. I'd do 11 on the bottom. Has 11 neutrons, so the top left needs to be my total mass number, which is 11 plus 11, or 22. I also see no indication of a charge, so this particular sodium is 2211 Na, okay? I'm going to ignore this third one because that one is an example of an ion, and I haven't taught you guys that, and I don't want to confuse you without doing it. So we'll do that once we get to that slide, okay? So atoms in general, like we said, are what they are. They have, around a normal mass, or a mass that you expect for that element. They should have no charge, but that's not how the real world works, okay? Some atoms have more or less neutrons than a traditional one for that element. Some atoms have more or less electrons than a traditional one for that element. So it is possible to end up with different things, okay? If an atom gains or loses neutrons, it heads down this left path, okay? That means that it creates an isotope. There's that word showing up. It has the same number of protons and electrons as the traditional atom, but now it has a different mass because I have a different number of neutrons. Just like on the previous slide, the mass number is reliant on the number of protons plus the number of neutrons. So if I have a different number of neutrons, that means that I'm going to have a different mass for that particular atom. Heading down the other path, if I were to gain or lose electrons, electrons have a charge, okay? And what that creates is an ion. So when I no longer have the exact same number of protons and electrons, meaning I no longer have the exact same number of positives and negatives, I'm going to have a different charge, okay? I'm going to have some leftover positives or some leftover negatives. And we'll kind of practice with that a little bit as we move forward into our practice, but what that basically might look like is, let's say I had 2 protons and 3 electrons, okay? Well, if I pair that up, I'm left with a negative charge. That negative charge now becomes the charge on the atom, okay? So whatever isn't used up, if I were to match up the protons and electrons, is going to become the charge on the atom. That's an ion. So if I had a sodium that had an extra electron, I would write it as Na, and I would put the charge up in the top right corner, +1, okay? Or if I had an extra electron, rather, bloop, 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 then I would have -1, okay? So if I had an extra proton, it'd be a +1. If I had an extra electron, it's a -1. If I had 2 extra electrons, it's -2. If I had 10 extra electrons, it's -10, which isn't going to happen, but you get the drift, okay? So as mentioned, anytime you increase or decrease the number of neutrons, you change the mass of the atom. And as a result, you are creating an isotope of that atom, okay? You're not changing the protons. Remember, we classify elements by protons. So by changing the neutrons of a carbon atom, it's still carbon, okay? But it's now a carbon isotope. It's something slightly different. It has a different mass, okay? So looking at the example down here, carbon with an extra 2 neutrons. Carbon typically has 6 protons, 6 neutrons, and 6 electrons. And we can represent that by calling it carbon-12 or C12. Okay, that is normal, traditional, most common carbon with a mass number of 12, 6 protons and 6 neutrons. Let's say we had an isotope of carbon with 8 neutrons. That means that if I add my 6 protons and 8 neutrons, I get carbon-14 or C14, okay? Looking at the diagram down at the bottom, you can see that C14 is not very common, but it is a type of carbon that can exist, and so it is an isotope of carbon. As a result, it does get factored into the mass of carbon, so carbon-13 and carbon-14 are what change carbon-12, or is what makes carbon's average atomic mass 12.011, okay? That slightly higher than 12 because there is some carbon-13 and some carbon-14 out there. So once it all gets averaged together, that's what happens, okay? Again, if average atomic mass is confusing you, ignore it for right now. Just recognize that it is taking into account all the possible types of that element when it is calculated. So as mentioned, if we gain electrons or lose electrons, we change the balance of the protons and electrons. If I lose electrons, then what that means is I end up with more protons than I had electrons, okay? So let's say I have 3 protons and I lose an electron, so I only have 2 electrons now, okay? When I match those up, I have extra positives. That creates what we call a cation. And I remember that because I like my cat, so cats are positive, so that's how I remember that cats are positive. Also, the word cation has a plus sign in it, the T, so that's an easy way to remember that it's a positive ion. The other side is the anion. When I gain electrons, so let's say again I had 3 protons, and I gain an extra electron, okay? When I cancel out everything, I have a leftover electron. That creates a negatively charged ion, which is known as an anion. And anions, I kind of remember that because it kind of looks like onion, and some people actually accidentally pronounce it anion, and it gets really weird. But when that negative charge is on that ion, it becomes an anion, and so the number of protons in that case is smaller than the number of electrons. So whatever's left over when I match up my protons and electrons, that becomes the charge of the ion. Okay, so we talked about atoms, we talked about how to read the periodic table, we talked about calculating and determining how many protons, neutrons, and electrons are in an atom. And then we took the next step of saying, okay, well, what if it's not a perfect atom? What if I've gained or lost neutrons? That creates an isotope. What if I've gained or lost electrons? That creates an ion, okay? So what I want you to do is on the bottom of your Cornell notes, which you should have been taking, I would like for you to write a little summary summarizing kind of what I just said right then, those main points, the things that we talked about in this section, okay? Summarize, I am checking your notes, so please make sure you have those in class, and I will see you next class.